Pluto, once recognized as a distinctive and valid planet in our solar system, was for many years considered a special entity. However, in recent times discussions led by renowned astrophysicists Neil deGrasse Tyson and Michio Kaku have placed Pluto back under scrutiny, sparking renewed interest in its status. These experts have proposed that Pluto may be on a possible collision course with Neptune, a theory that has stirred up many questions. How could such a massive impact take place? What would the consequences be for both planets and for the solar system? Are we witnessing a strange cosmic phenomenon, or is there a more intricate and profound explanation behind this idea? Let us explore what such a potential Pluto-Neptune collision could mean for us. Once seen as a smaller, more distant object in the solar system, Pluto continues to generate a great deal of interest among scientists. According to significant studies from leading professionals, Pluto's orbit is dangerously close to Neptune's, and this has led some astrophysicists, including Tyson and Kaku, to raise alarms about the possibility of a catastrophic crash between the two bodies. The looming question now is, could such an event present a real risk to Earth? How could it even happen? Pluto's orbit is one of the most unique in our solar system. It takes an extraordinary 248 years to complete a single orbit around the Sun, which means that since its discovery in 1930, Pluto has yet to finish one full cycle. However, that's not the only peculiar feature of Pluto's orbit. It is elongated in shape, unlike the more circular orbits of the larger planets. Furthermore, Pluto's orbit is tilted at a 17-degree angle compared to the plane of the solar system, making it one of the most tilted orbits observed in space. This extreme tilt paired with its irregular shape adds complexity to its journey through space. One particularly intriguing aspect of Pluto's orbit is its interaction with Neptune's orbit. For about 2 decades during each orbit, Pluto actually comes closer to the Sun than Neptune does, defying expectations about the relative positions of these planets. This brings up a crucial question. Why haven't Pluto and Neptune collided? The answer is found in the gravitational forces at work within the solar system. Pluto's orbit was a mystery to astronomers immediately after its discovery. Unlike the other planets whose paths remain nearly flat and aligned along the solar system's plane, Pluto's orbit was tilted and elliptical, making it a subject of intense study. The fact that Pluto's orbit crosses Neptune's doesn't automatically mean a collision, thanks to a gravitational interplay that stabilizes both orbits. This balance, known as the three-body problem, refers to the way three celestial bodies, Pluto, Neptune, and the Sun, interact through their gravitational pulls. Essentially, it's like trying to predict the future paths of these bodies by accounting for their current positions and the gravitational forces they exert on one another. In Pluto's case, this phenomenon reveals how its orbit, Neptune's orbit, and the Sun's gravity all work in a balanced way to prevent a collision. Astrophysicists have pointed out that the stability of the Pluto-Neptune orbital interaction is helped by a mechanism called libration. In this context, when Pluto crosses Neptune's orbit, it does so at a distance of at least 90 degrees away from Neptune, meaning that the two bodies will never be in the same place at the same time. There's also the phenomenon of degree libration, which refers to the oscillation or shifting of Pluto's orbit around its path. This means that Pluto doesn't cross directly into Neptune's orbital plane, further minimizing the risk of a collision. Another important factor contributing to Pluto's orbital stability is a gravitational wobble phenomenon known as VZK wobbling, named after the scientists who analyzed how celestial bodies move in space. This effect explains how Pluto, Neptune, and the Sun influence one another's motions through gravity, helping keep Pluto's orbit stable. Despite Pluto's seemingly erratic movement, the combined forces at work ensure that its path remains relatively consistent over long stretches of time. The three-body problem and the forces governing these celestial motions are crucial for understanding how planetary orbits evolve over time. These interactions between Pluto, Neptune, and other bodies allow us to learn more about not only Pluto but also the broader workings of our solar system. Numerical simulations conducted in the late 1980s revealed that although these stabilizing forces help maintain Pluto's orbit, slight variations in its initial conditions could cause its orbit to become more erratic over extended periods. However, despite these potential irregularities, Pluto's orbit remains relatively consistent over the millennia. Recent computational models have further illuminated the ways in which Jupiter, Saturn, and Neptune stabilize Pluto's path. For instance, Neptune and Pluto are in a resonant orbit, meaning that for every 2 times Pluto orbits the Sun, Neptune completes 3 orbits. This resonance is crucial for maintaining the stability of Pluto's orbit. However, Neptune is not the only planet that influences Pluto's path. Jupiter's gravitational pull also plays a significant role. Even Saturn has been shown to contribute to the stability of Pluto's orbit. These simulations suggest that the gravity of Jupiter alone is powerful enough to maintain Pluto's trajectory for billions of years, if not indefinitely. The cooperation between Neptune, Jupiter, and Saturn is therefore crucial in ensuring that Pluto remains on its stable orbital course. Without these stabilizing forces, our solar system would be far more chaotic, with objects like Pluto potentially colliding with other bodies or being flung from their orbits entirely. Leading astrophysicists, however, have recently raised concerns about a potential collision between Pluto and Neptune. Neil deGrasse Tyson, a prominent astrophysicist, offers a fascinating perspective on the mysteries of our solar system using Pluto as a case study. Tyson, who played a key role in reclassifying Pluto from a planet to a dwarf planet, emphasizes the importance of continuously evolving our understanding of celestial mechanics. Tyson views Pluto's unusual orbit and its interactions with Neptune as a testament to the unpredictability of space. While he acknowledges that Pluto's orbit is stable for the time being, he warns that it could change significantly in the future. This possibility highlights how much we still have to learn about the forces that shape the solar system and their far-reaching implications. Michio Kaku, another key figure in the discussion about Pluto and Neptune, offers additional insight into the potential risks and dynamics at play. His perspective builds upon the work of Tyson and others, exploring how even small changes in Pluto's orbit could potentially lead to a collision with Neptune or affect the stability of other celestial bodies. As scientists work to better understand the possibility of a future collision between Pluto and Neptune, they rely on sophisticated simulations and models to predict how the gravitational forces acting on these two bodies will evolve over time. These simulations help scientists track the movement of Pluto and Neptune, taking into account the complex interactions between their orbits and the influence of other planets like Jupiter and Saturn. Despite the relatively stable relationship between Pluto and Neptune today, there is still much uncertainty surrounding the future of their orbits. Even the smallest variation in the initial conditions of their orbits could cause their paths to diverge, leading to potential collisions or other disruptive events. As we continue to explore space, the study of Pluto and other distant objects becomes increasingly important. These objects, though far from Earth, hold clues that could help us understand the origins and future of our solar system. The ongoing research into Pluto and Neptune serves as a reminder of the need for continuous learning in the field of astrophysics. In conclusion, the potential for a collision between Pluto and Neptune is a fascinating and complex topic that continues to captivate scientists and the public alike. While the current stability of Pluto's orbit is reassuring, the possibility of future changes serves as a reminder of the unpredictable nature of space. As we continue to study Pluto, Neptune, and the other objects in our solar system, we gain deeper insights into the mechanics of our cosmic neighborhood, insights that will shape our predictions for the future and enhance our understanding of the vast and dynamic universe we inhabit. The future of Pluto's orbit and its scientific significance. While Pluto's current orbit appears stable, the long-term evolution of its trajectory remains an open question. Advances in computational modeling, astronomical observations, and deep space exploration continue to refine our understanding of how celestial bodies interact over vast timescales. Scientists are particularly interested in how external gravitational influences, minor perturbations, and chaotic orbital dynamics might contribute to shifts in Pluto's path over millions or even billions of years. One of the key areas of study is how planetary migration, the gradual shifting of planets' orbits due to gravitational interactions, could alter Pluto's relationship with Neptune. Historical models suggest that during the early formation of the solar system, Neptune itself moved outward from its original position due to interactions with the protoplanetary disk. If such migrations continue in subtle ways, even small changes in Neptune's position could influence Pluto's long-term stability. Furthermore, Pluto's classification as a dwarf planet places it within a broader category of trans-Neptunian objects, TNOs, which includes other icy bodies in the Kuiper belt. The study of these objects provides crucial insights into the solar system's formation and evolution. If Pluto's orbit were to shift significantly, it might also affect other Kuiper belt objects, KBOs, triggering potential collisions or altering their paths. The role of future space missions. Future space missions could provide direct observations to refine our models of Pluto's orbit and its interaction with Neptune. NASA's New Horizons mission, which flew past Pluto in 2015, provided the most detailed images and data we have on Pluto's surface atmosphere and composition. However, a dedicated follow-up mission could focus specifically on tracking Pluto's motion with extreme precision, allowing astronomers to test and refine theories about its long-term orbital evolution. One proposed mission concept is New Horizons 2 or a Kuiper Belt Explorer which could study Pluto and other KBOs over an extended period. By continuously monitoring Pluto's position relative to Neptune, such missions could provide critical data on whether its orbital parameters are shifting in ways that might increase or decrease the likelihood of future collisions. Additionally, improvements in ground-based and space-based telescopes such as the James Webb Space Telescope, jUST, and upcoming next-generation observatories will enable more detailed tracking of Pluto's movements. These observations, combined with computational models, will enhance our ability to predict how its orbit might change in the coming millennia. Broader implications for planetary science. The study of Pluto and its potential interactions with Neptune extends beyond the immediate question of planetary collisions. It provides a framework for understanding how celestial bodies interact in other star systems as well. Exoplanetary studies have revealed many systems where planets exist in resonant orbits much like Pluto and Neptune, suggesting that similar gravitational interactions are at play in planetary systems beyond our own. Moreover, understanding Pluto's stability offers valuable insights into orbital mechanics, chaos theory, and long-term planetary evolution. If Pluto's orbit remains stable for billions of years, it reinforces the idea that even seemingly chaotic systems can achieve equilibrium through complex gravitational interactions. Conversely, if Pluto's orbit is found to be gradually destabilizing, it could prompt new discussions about planetary migration, gravitational perturbations, and the broader stability of our solar system over geological timescales.